So we are continuing our description of random error or type A errors in chemical analysis. Disclaimer: this is not your mathematical statistics class. It's only application of basic statistical features in analytical chemistry. Please you so we have one measurement x1 with mu, mean, and sigma, standard deviation. They exist, we just do not know them, but they always exist. There is distribution of error of any our measurement. So we did measurement 1. Next, we are making second measurement of exactly the same value with exactly the same method. So mu should be the same and sigma should be the same. The only problem, we do not know them. We need to estimate them. It has the same mu. It has the same sigma. So how we estimate mu? As estimate of my unknown mu, I will use an average. Average of two numbers is number 1 plus number 2 divided by 2. Now, what about sigma? Sigma of sum of two numbers will be sigma of first squared and sigma of second squared. But these are the same because it was the same value, just taken twice. So it's twice sigma squared, or if we take square root of 2 multiplied by sigma, where sigma is standard deviation of first or second measurement. Now, average is result of addition divided by exact number 2. This is exact number, so it has no error. So we are just dividing everything by this number. Square root of 2 divided by 2 is 1 divided by square root of 2. So the result of average is sigma divided by square root of 2. Now, what's important? Square root of 2, of course, is a number that is larger than 1. So standard deviation of our average, of our estimate, is smaller number than standard deviation just of one measurement. We can do very similar calculations for more measurements. If I am taking n measurements of the same value, my average will be measurement 1 plus measurement 2 plus measurement 3 all the way to measurement n, and we divide it by the number of measurements. Now, similar to previous example, we can calculate that for this number, standard deviation will be standard deviation of one single measurement divided by square root of n, where n is number of measurement. It's very important. If I do more measurements, I am reducing standard deviation of my estimate. I know my number with better precision. Uncertainty is becoming smaller. So let's apply this knowledge to our case 3. We know standard deviation sigma from somewhere. So what's real value? And how good is our estimate of real value? We are taking n measurements as before and calculate average as we always do. X bar is measurement number 1, measurement number 2, until measurement number n divided by number of measurement. Now, what is our estimate of error? I look at a table with 95% probability it should be 2 sigmas, but sigma of my measurement was sigma of single measurement divided by square root of number of measurements. So my mean, my estimate is x average plus minus 2 sigma divided by square root of n with 95% probability. Please take into account if you are using other probability than 95%, this number will be different. So for 97 probability, 99.7 probability, you need to put 3 sigma. If you are okay with 68% probability, you are just putting 1 sigma. This interval from smaller number to larger number we name confidence interval, and that's how we read it. This is our result for randomly distributed measurements. Next case. What if I do not know standard deviation? So I am looking for mean and I am looking for standard deviation taken from my own measurements. What I do? I take n measurements, calculate the average as usual, first, second, last divided by number, and I calculate standard deviation myself. It's not sigma, it's S. So first measurement minus mean, second measurement minus mean, all of them squared, and I divide it not by n but by n minus 1, where n is number of measurements. So how can I calculate confidence interval from this and this? I do not know sigma. I only have S as my estimate. This problem was solved by Irish mathematician Rosset, who wrote under pseudonym Student. So we name this student statistics. Student is not student, it's simply a name. So for 95% probability, we are not using 2 in this case. We are using a larger number, which depends on number of measurements we did. If we did just 1 measurement, instead of 2, I need to write enormous number of 12.7. For 3 measurements, it will be 4. For 10 measurements, I will be very close to 2. For infinity, I'll have the theoretical value before. Now, we do not use the tables anymore. We have a function in Excel that helps us to calculate, or we can do other mathematical tools. So, how we do our calculations? Again, we do not know mean, we do not know standard deviation, we have our n measurements, and we have our x average and estimate of standard deviation. Now our confidence interval will be very similar. So it's mean plus minus. Instead of 2, I am writing student's coefficient with 95% probability and number of measurements n. So this is a function of two parameters. Instead of sigma, I am writing standard deviation. Here it's square root of n. So this is my new confidence interval for the case when I do not know standard deviation and I calculate it myself. So as a summary, for known standard deviation with 95% probability, my result will be x average plus minus 2 sigma divided by square root of n. For unknown standard deviation S, I calculate average and estimate of standard deviation, and again with 95% probability, my result will be x average plus minus student's coefficient multiplied by my estimate S and divided by the same square root of n. Keep in mind that T95 will be always larger than 2. Why we name it confidence interval? Just a reminder. So my result is x bar plus minus T95. What does it mean? Plus minus. The value of x is located inside the interval. So we have smaller number, x bar minus T95 multiplied by s divided by square root of n, and bigger number, x bar plus T95 multiplied by s square root of n. So this is our smaller number, this is our x average, and this is our bigger number. What confidence interval says that with 95% probability we have our mean located between this and this number in this interval. Again, if I change probability from 95 to different number, I need to change student's coefficient, and then it will change the confidence interval. Of course, if I want higher probability than 95, my interval of uncertainty will be larger. Why 95? That's common answer for routine calculations. More part of tradition, but many of your customers will require different probability than 95. Then you need to recalculate students' coefficient and have different confidence interval. We'll look at more examples of these calculations next.